We want to finish by touching base on just some other practical issues that come up with redox titration. So the first is that when you're running redox titration, you are usually doing these in the presence of high concentrations of strong acid or base. So in the flask, you're going to add enough like strong acid or strong base to make the pH like 0 to 1 or 13 to 14. The acidity affects the chemistry occurring. So, when we were doing balancing, were you balancing under acidic conditions or basic conditions? So you're kind of really making sure you're pushing one way or the other for your redox chemistry to be happening under either very acidic conditions or very basic, whatever it is that you want to do. It's either way works. And so this isn't just like for balancing. It does also functionally affect the oxidation state that is preferred. So if you start with, say, you put your MnO4 minus, your permanganate, and you allow it, you're going to use it as an oxidizing agent, so it's going to undergo reduction. It can either take 5, 3, or 1 electrons. And then you either get Mn2 plus, which is the +2 oxidation state, +2, that one's colorless. You can go to +4, that one's brown, or you can go to a +6 oxidation state. That one is, I think, yellowish. And so all of these are potential changes, but which one is favored can be affected by how much acid is present and what the relative pH is. So if you have a really highly acidic solution, you get this top one. You go to Mn2 plus when the pH is like less than 1 or 0, right? Very high concentrations of strong acids. If you have, say, like a weakly acidic solution, like pH of 3 to 6, you're going to end up at MnO2. And if you have a basic solution, you're going to get a strongly basic solution, like above 14, you're going to get MnO4 minus. If you're not in that range, you get a mix. And so that's why you only want to focus on the ranges where you get a single product. And so the reason why, so like when we did our example, we like balanced things under acidic conditions because we were doing this. We were imagining we had thrown a bunch of strong acid in there. So, we were basically dealing with a pH of +1 or less than 1, very, very highly acidic. And the reason is we wanted to get, remember, to this colorless Mn2 plus. So we were pushing to get down to that Mn2 plus. So when you're using permanganate in redox titration, you almost always use highly acidic solutions. That way you get that color change from purple to color. So I have that as the indicator for when you're done. And so that's, we know that along those lines, when we're using permanganate, we get those nice color changes of the metal that works for indicating that where we've reached the equivalence point. If you're using a reducing agent, though, how do you indicate the equivalence point? These things do show some color changes, but they're not as strong because you'll note there's no transition metals in there. And so we need to use something else. We use basically an indicator. So what we'll do is we'll look at an example of how this would happen. So say you want to titrate chlorine, Cl2. So this actually happens all the time. You use chlorine in, say, wastewater treatment. So you add chlorine to kill, living things, sanitize water to consume it. And so this always has to do, because you don't want, if you use way too much chlorine, you don't want humans drinking that chlorine. So you want to measure the chlorine that's left over in water. So Cl2 is a pretty good oxidizing agent. It really wants to oxidize. So we're going to titrate it with a reducing agent. So we want to use a reducing agent. And whenever you see that you need to use a reducing agent, that's an indication you're going to need to use an indicator, because the oxidizing agents, those were the cerium, those were the manganese, those have the color they change, the burette will be a different color than your flask, and you'll be able to use that. But you need to use a reducing agent. And so the direct titration of Cl2 is going to be relatively hard here. It's a really low concentration, so the color change will still be like really, really faint. So it ends up, if you're trying to do it naturally, it's going to be tough. So instead, we use what's called indirect analysis. We're going to titrate something else, and this is actually really, really common when you learn that you need to do a titration with a reducing agent, because it's really hard to get a color change, you're going to kind of flip the script and do your titration in a different way, a different kind of indirect analysis.
So we're going to walk through this process. I want to titrate my solution of Cl2. So I got chlorine in my solution, and I want to titrate it using a reducing agent. So what I'm going to do is I'm just going to add a bunch of my reducing agent. In this case, this will be Ki. I'm going to add excess, I'm going to add a bunch to react all of my chlorine. When I put the Ki in, so I just dissolve it in, fill my solution with that. There's, again, lots of Ki in the solution. It's a salt. So it's going to separate out into the ions, and the iodide is what I really want in there to do my chemistry. So the I- is going to be a reducing agent, and will reduce the chlorine. And so it's going to react with the chlorine to form I2 and Cl and chlorides. And so now I have all these I2 molecules floating around in solution that are now in there. And this would be the number of I2 molecules is going to be based on the number of Cl2 molecules I started with. Because I can see that I'm still going to have these iodides in there, right? I added extra iodide, that the I-, that they're still floating around in there, but I have only the I2 that has been generated in the reaction with the chlorine. And so the solution will now be brown. These I2 molecules have a brownish color, unlike the iodides. So if I had iodide, it would be an entirely colorless solution. A solution of iodine is kind of brownish, reddish, brownish, yellow, depending on the concentration. And so there is a distinct color change between these. So the overall idea is we can now titrate the I2. We're going to figure out the amount of I2 molecules in this flask and relate that to the amount of Cl2 molecules that were initially in the flask. And you can just do a color, because you have a color change here, you can just titrate this solution, but it's really hard to do. And the real reason is because you're trying to see a loss of color. Right? As it stands, you have a brown solution. As you titrate, as you remove the iodine, the I2, it will become the colorless iodide. And that's actually going to be really difficult to see. In the other examples with the manganese, you were looking for colorless, and then you wanted to see the first time you saw color. So that's kind of, you're looking for a change. But in the case of going from brown to colorless, it's actually really hard to identify where it is or what it will look like. The equivalence point will actually have kind of a yellowish tinge to it, just with how iodide, the I- is reacting naturally with water. And so you want to, it's really hard to get this. So we need to add something else, an indicator molecule, that we'll see a bigger color change. So that is starch. So just starch like from food, starch, potato starch, just sugars from plants. And the reason is I2, when it's in solution with starch, turns dark blue. So any amount of I2 will be extremely dark blue. And it's a really sharp color change that you have if you have, like any I2, you get this really, really dark color. And then the minute all the I2 is gone, it's perfectly colorless. So it's a really sharp change. You are still seeing a disappearance of color, but it's not gradual like it is for normal iodine, where it's that kind of slowly fading out of brown to red to yellow. Instead, it's dark blue to colorless. And so it's much easier to see it immediately. So now that we have our solution of I2 and we've added the starch so that way we can see the color change that's going to be happening, we actually do the titration. And so to do the titration, you need to use a different reducing agent. So our first reducing agent that we were using, right, was we added all this extra iodide. And so that reduced our initial chlorine. Now we need to add something that's an even stronger reducing agent. S2O3, 2-, that's called thiosulfate, is the most common choice. It's a pretty stable reducing agent that it won't degrade in your lab, but it does work. And most importantly, it's common here because iodine is really, really common. This setup with iodine is really, really common. And S2O3 can reduce iodine back to iodide, so I2 to I-. So thiosulfate, S2O3, is the most common choice. And so when you're actually doing the titration, so you add in the S2O3, so you would take this, you'd add it into your flask, and slowly you would be reacting these I2s. They would eventually go away, and all go back to I-. And that color change will be really quick because of the starch. So you can see in this example here, in this GIF, this person is adding, so you start out with this dark blue solution. He adds 1 drop of the S2O3, 1 drop of the thiosulfate, and then it goes colorless. So it's a really, really sharp color change. It's not a slow, gradual color change. It goes from, opaque, blue, dark, to completely colorless. So it's really sharp. That's what we want. That's where the equivalence point happens, where we lose that blue color. So when you actually do your titration, what you actually titrated was the I2. You figured out the concentration of I2 that was in solution, right? You figured it out based on the concentration of S2O3 and however much you added, and then you can figure out the I2 based on, after you balance this equation, you can figure out the amount of I2 that was in solution. Then you use stoichiometry to relate that to the concentration of Cl2, because basically the I2 that formed was based on the amount of Cl2 that was initially in the solution. So it's a little more complicated than the direct titrations that we've done. It's indirect titration. You don't directly titrate the chlorine. You instead turn the chlorine into iodine, the I2 molecules, then you titrate the I2 molecules. This is very common, especially in reducing agents. Doing these with these iodine is a really common technique. Iodometric titrations are what we call these, where you're using kind of this, you're titrating, you really want to titrate chlorine, but that's hard. So it's hard to do a titration of chlorine. So instead you do kind of a more complicated process with more complicated calculations, but it's an easier titration because the titration of iodine is at least straightforward and possible because of starch. You can get that really sharp color change. Chlorine, you're just not going to see much of a color change at all from it.
So if you don't want to use color change, you can also use voltage to measure the progress of a redox titration. So you're measuring what's called the potential. This is a measurement of the flow of electrons in these sorts of redox chemical reactions. And we'll touch more on this as we move through this chapter. But this is just a number that you can use that is characteristic of the ions that you have in solution. The thing is, it's a more complicated process than just running the titration. Basically, you run the titration, so you have like your flask and your burette, but then you also have this other side reaction that's either in a different container, or you have like some extra probes you put into this, and there's contained solutions. So the chemistry gets quite a bit more complex, as if it couldn't. But what you get is you get this measurement of basically you're adding in CrF4+. And so the volume of cerium-4+, you basically just have this measurement of the voltage. And you can see that basically this overall graph, we can get these measurements of potential that is characteristic of iron. So it tells us that we have the iron things in the flask. There are also potentials that are signature of having the cerium cations in your flask. And so those are up there. One important thing to note, unlike pH, it's not like you just have basic pHs. You have basic pHs, low pHs, or acidic pHs. When you're dealing with potentials, it would be cerium potentials and iron potentials. So they are characteristic of those particular ions that are in the solution. And so you would need to know what those values are for those particular ions. And for certain titrations, they sometimes could potentially line up and this process wouldn't work, or they'd be close and it'd be cloudy. But you'll notice there is a jump where the switch happens for what is the dominant kind of species, what is the major things that are in solution that are driving the chemistry that's characteristic. And that switch happens when at the equivalence point. So similar to the pH graphs that we saw with acid-base titrations where you get a jump, you also get a jump in this potential or voltage when you're doing a redox titration. This change in the potential can also affect other molecules that are indicators for redox titrations. And so just like we saw with acid-base titrations, when you're dealing with redox titrations, there are molecules that have they get affected by the redox chemistry and they change colors if they're oxidized or reduced. And so you can use different molecules that cover different ranges that they change color at different potentials. And so, for example, diphenylamine sulfonic acid changes colors at 0.85. It goes from colorless to red. And so this reddish purple color. So you can see like down here, your solution, this sort of fade is indicating colorless. And then basically, you've hit the equivalence point when it goes to red. So when the color changes, you'll also see ferroin is a different dye that's going from red to blue as the potential increases. And if you remember, these potentials up here, these 1.6-ish potentials, are indicative of having this CE3 plus and CE4 present. You're past the equivalence point. And so when you're doing cerium-based redox, the equivalence point tends to happen close to 1.6. And so ferroin you can almost always use when you're dealing with C4 plus titrations. If you're going to use cerium, you can almost always use this ferroin dye. And again, this is again, it's one of those things I'm not expecting you to memorize how to do these things or that there are these levels, just to know that doing redox titration is a bit more complicated than acid-base titration. There's a bit more factors to it. There's also more flexibility. So, you have to figure out more things, but you have more flexibility. What are you dealing with? What's the best strategy? Are you going to do one of these indirect analyses? You're going to do a direct analysis. Are you going to monitor potential? Are you going to monitor the color of your manganese? Do you need an indicator? There's all sorts of things going on that you need to know the answer to, but they also offer different variables that you can change to engineer. So there's a lot of flexibility to do. I don't expect you to memorize or have all this stuff, but just know that these sorts of flavors are there, these sorts of complications as well as opportunities to design the exact experiment that you want, or need, rather. Another video down, just one more in this set. All done with redox titrations. There's a video about the big topic that we'll cover basically all of next week. Participation 11.7 is what we're looking for questions on. Maybe more videos in that final question. Maybe more questions in the final video. See you there.